Okay, so we're on to nuclear physics now. Just select topics here. There's really four different types of problems here. So the first one and the easiest of these is just estimating nuclear sizes. So this is the equation. I'm just going to use an equal sign, even though it's an approximation. Is this constant here, which is kind of like the radius of one proton, if you will, times a to the 1/3 power. So it grows as a volume. That's why it's a 1/3 power. Um, Now we do have to say something about the notation here. So x is the element symbol. I'll put z first. Z is the proton number, so it's the element number, and a is the nucleon number, which means neutrons plus protons. But for all these problems, these are going to be sort of provided. Okay, so estimate the first one here. It's not really much of an estimate for H11. All you need to do is figure out what A equals. Well, that's 1. So for hydrogen, it's just 1.2 times 10 to the negative 15th meters, which is the size of a proton, which that's what H1 is. Remember, we're talking nucleus, not the atom itself with the electrons and everything. For U, 238. Sometimes you'll see this without the other number, but I wrote 6 there. U 238, A is 238. So one of the biggest nuclei. Um, so 238, but you see it's to the 1/3 power, which is the same as the cube root. So the way I do this, um, okay, there's 1.2 to the negative 15th times, and I'll do parentheses 238 to the parentheses 1/3 power. And so we get 7.4 times 10 to the negative 15th meters. It's not really that useful to know that, but it is a type of problem. So as an example there. Okay, 30-4. Now we're getting into the really unusual part of nuclear physics is that, so for example, this one we're asking for binding energy for iron. So basically what we're doing is we're taking the mass of iron, okay? So this is Fe, I'll just write it here, Fe 5626, okay? That means 26 protons and what, 30 neutrons, okay? And 30 electrons. Not 30 electrons, 26 electrons, okay? Now the neat thing about nuclear physics is that when you take the mass, and these are all just measured, the mass of iron as a nucleus, okay, hold on a second. You know, this is, sometimes I'll have to stop here and make sure I know what I'm talking about. Okay, the electrons are there. You'll see as we go through in the problem why they're there, but we shouldn't. I'm not going to include them in this first. You know, I'm introducing this topic for all these examples. Okay, so just the nucleus all together, all the protons and neutrons together, and then separately on their own, what we call a bare particle. Okay, bare particle. If you take this mass, okay, compared to this mass, all these added up, okay, actually have more mass than when they're all together. Why that is very hard to explain, but the binding energy itself takes some of the mass. Um, as a form of energy. It's kind of the best way I can explain it in a single sentence. You don't really need to know any of that to do these problems. If you're interested, definitely read up on it. Um, I'll just focus on how to do the problems here. Okay. So basically, what we're going to do to get the binding energy, okay, we want to take all this, the mass of, we'll call that 1, and subtract the mass of 2. And whatever's left over, that's the total binding energy. Okay. Now the way we can do this, and the way the example does it, I'll just follow along, is it takes 26 times the mass of H11. Okay. I'm just going to put this like this. Plus 30 times the mass of a neutron. Okay, equals something. That includes the 26 electrons. Okay, sorry, got to subtract here. And then I subtract the mass of this one, which also includes the electrons. So we add the electrons here, but we subtract them right back off here. And that's just, I think that's just because how these are listed in the back as for atoms instead of nuclei. Okay, but this is just the process. So 26 times the mass of hydrogen. This is all in Appendix B if you need to look up. Now, the masses are given in these units of U, atomic mass units. So instead of like kilograms, we just stick with U's because the numbers are more manageable than like 10 to the negative 27ths and stuff like that. And then minus, I'll put it down here, minus, and this is from the back. Okay, and you'll see that this comes out, it doesn't come out to 0. You might expect it. If everything is here and everything is here, it comes out to 0, but this weird quirk in nuclear physics where when you pack stuff into the nucleus, it has a smaller mass than when they're bare. And this comes out to 0.52846. And you really have to, go with as many decimal points as you can here. Okay. Now that's not an energy, that's a mass. Okay. Now to find the energy, you take your mass you just found and you multiply it by this conversion factor, this 931.5 mega electron volts per U. And this is like 492.26 MeV. So MeV is kind of a standard unit for this. Like if we tried to use joules, these numbers would be incredibly tiny. Okay. Now that's total, so per nucleon, I'll try to put it here. Take your answer, divide by the number of nucleons, which for iron is 56, and 8.79 MeV. Okay. So anytime total binding energy or binding energy per nucleon, just follow the steps in 30.4. Okay, 30-5. Okay, now it says, for C, for carbon, 13.6, what is the binding energy of the last neutron? The last neutron. That's a terminology. That means if you were to take away one neutron, how much energy would it take? Okay, and we're going to do the same thing here. Okay. Now this is C13, which is not the normal. The normal carbon is C12 plus a neutron. Sorry. The normal carbon is C12. So C13 is C12 plus a neutron. Okay. So we're going to do the same thing here, where we're going to do the mass of the constituents, which are these two, have a higher mass than this one. So it's these two minus that one. Okay. So in terms of masses, C12 plus a neutron in terms of mass minus C. Okay, and you'll see for all these problems it's the same thing. It's the all the masses of the constituents added together minus the original thing. And again, we can look these up in the back. That's zeros all the way for that carbon. That's actually how its mass unit is defined. And then plus, we'll do a neutron again. And then minus, again in the back, looking up carbon 13. Okay, now this is total, it is for one particle. Okay, we still have to multiply this guy by the 931.5 to get it into MeV. Okay, this should come out as 4.95 MeV. Got off the screen there, but you can see it's just writing out the answer there. Okay, let's see what's next. 30. Did I say 30-6? Okay, we don't need to do. There's no homework based on 30-6. So you would do the same thing, but for uranium, and I'll just say here an alpha particle is a helium-4 nucleus. Okay. So it's A is 4, 2 protons and 2 neutrons. Okay. Now, again, this is going to seem similar, but we're getting into the types of decay. So alpha decay, that's the helium. Beta decay is when you lose an electron. Okay. So we have C14. How much energy is released when C14 decays to N14 by beta emission? So I'm just going to go here. So C14 becomes N147 plus an electron. Beta can also be positive, but we're not going to do any problems with those. How much energy? Well, we're always still the same process, you know. The masses of these added subtract the mass of that. So the mass of N14 plus the mass of an electron minus the mass of C14. Okay. So we got, let's see, 14. Okay, hold on. This might be a little different here. Go back a little bit here. Okay, we want to know how much energy. Well, it should be the same process. Let's just do it the same way and see if it works out. I'll say it's quite late on a Sunday now, which I wanted to get these videos out by Monday, so that's why I'm doing it on a Sunday night. So bear with me here. That plus the mass of the electron. Let's see, where's that? I have to look in the front of the book here. Okay, mass of electron. Okay, 0.000549 minus the carbon 14. You know what? I'm gonna skip this one now. I'm gonna wait and do a special video on that one because I just cannot think right now. So let's we'll skip that one for now. Okay. Now we get into something. In the chapter it goes through the types of radioactive decay and the fact that when something undergoes a radioactive decay, it changes from one thing, one element to another. So even in this one, your sample starts changing from carbon to nitrogen, and it happens at a specific rate. Okay. So I think let's just get into the example, and I'll sort of explain the process and the symbols and stuff as we go. Okay, so 39. The isotope C, I just like to write these down as I'm going. So C14 again has a half-life. So I'm going to write this as T half like that. Okay, if a sample contains, now this is going to be capital N. This is 1 times 10 to the 22nd power nuclei. That's how many nuclei I'm starting with. Okay, so I have number of nuclei, half-life. Now, any number of nuclei basically means half the sample is going to decay in 5,730 years. So I can just make that statement that if I create this sample now, in 5,730 years, I'll have 5 times 10 to the 21st, half of this, right? Nuclei. But we want to talk about this sample now, meaning some nuclei are decaying immediately, just at a rate, that will reach half the sample at that time. Okay. So the activity, which is defined as the absolute magnitude of the change in the number of nuclei divided by the change in time, and this is equal to lambda times the number of nuclei at any time I choose. As long as I know the number of nuclei, multiply it by lambda, where lambda is called the decay constant, and it's related to the half-life by the natural log of 2 over the half-life, which is roughly 0.693 over the half-life. Half-life. The half-life is in time units, so the decay constant is in inverse time units, which means we multiply it by here. This gives us number of nuclei per a unit of time, and that's the activity. So R is the activity. Okay, now once we have this, it's fairly straightforward. So basically I'll plug in, I need to calculate lambda first. Of course, I need to convert this to seconds. And I'm just going to use the example here as seconds per year there. Okay. Now what does that mean? That means basically the time it takes for one nuclei to decay. So it's a very short time, because we're talking about, even in that number of years to decay that many nuclei, half of them, it's 10 to the 22nd power. That's a lot of nuclei. So it's going very fast, even though it takes that long. And then R is just lambda times N. And so you just multiply lambda here times our number of nuclei. Sorry, activity is the decays per second. Yeah. That's the time between decays. This is how many are, so even decaying 10 to the 10th power per second, it takes that over 5,000 years to decay up to 10 to the 22nd power. Okay, where am I at? That was 39, so 3011. Okay. So for 3011, so we have 1.49 micrograms. So we're dealing with N13. So 1.49 times 10 to the negative 6 power grams, which has a half-life of 10 minutes, 600 seconds. So T1 half, 600 seconds. How many nuclei are present initially? Initially, so I'm going to call that N naught. Okay, so think, if we know, we kind of have to deal with moles here. So remember, if we take our mass in grams, divide that by, for nitrogen, 13 grams per mole. Okay, and then multiply by Avogadro's number, which is particles per mole. Okay, everything cancels out, right? So put this 1.49 10 to the negative 6 grams there. And this gives us number of nuclei. That's more of a chemistry thing to me, but just try to follow. So basically, mass in grams divided by grams per mole for the substance, which in this case is the 13 there, and then multiply by Avogadro's number. Okay, so Avogadro, however you'd like to say it. Okay, so the next part then, B, is what is the decay rate, which means find the activity. So this is the same as the previous example, where I'm going to put it R naught because we're going to decay this over time, so we need to know the initial values. So same thing. Okay, so 0.01155 inverse seconds there, and then the activity times the number of nuclei we just found. Okay, and that's decays per second. Okay, now part C. What is the activity after 1 hour? So now, because the number of, the activity depends, this doesn't change, lambda doesn't change, but N will, because N immediately starts going down, so the activity starts going down as well in sort of an exponential way. Okay, so that's the decay law. And we have everything we need to know here. R naught is what we just found. If you look at this function, basically it starts at 1 for a time of 0 seconds. E to the 0 is 1. So at a time of 0, that's our initial. But because it's a negative, as t gets bigger, e, or this whole term, gets smaller in an exponential way. See, where's lambda? That's why the negative is there. In 1 hour, so 3,600 seconds. So it'll be some percent, this will come out as some decimal between 0 and 1. Let me do that first. Okay, so that's 0.0156. Okay, so basically 1.5%. and then times our okay. So that's how many nuclei we have left after an hour. And you might say, that's not that different. But if you look at it, 10 to the 12th, and this is almost 10 to the 14th, right? So 10 to the 12th is 1% of 10 to the 14th. So this is, it's 1.5%. And let's see. After approximately how long will the activity drop to less than 1 per second? Okay. So I'll go through this first, but because we have a power, we have to use the natural log. So natural log of both sides. Natural log here. So the natural log of r over r0 equals negative lambda t. So t, natural log of this ratio over, let's see, negative over lambda. So this r over r naught has to be less than 1. The log of anything less than 1 is going to be a negative. So the negatives cancel out. Let's see what we got here. So r, now it's going to be, basically we want to find if r is 1 dk per second divided by the original. Let's see, where was that? No, that's the wrong answer there. So over lambda, this point 0.001155. The units get all tricky here. Basically, take this ratio first, then take the natural log. If you can tell, I like doing my problems in steps so I can see what's happening as I go. It's easier to catch mistakes that way. Now just natural log of that. See, negative 32. And that negative there means this is a positive answer. So this is 27,713 seconds. And that's around 7.7 hours. Okay, let's see. That was 30-11. We got one more. 30-13. There's one homework problem that's basically exactly this example. This is carbon dating. Okay. So mass, and this is all dealing with carbon. So we got 200 grams. The current activity, 16 decays per second. What is its age? We know mass, we know activity. Now we're not told if this is C14 or C13 or C12 or whatever. This is all the carbon together. Okay. So the first thing is to do this same process where you're taking the grams divided by, now in order to get the number of atoms, we do use just 12. Okay. Instead of 12 point and then maybe 100 zeros and then some decimal. It's basically going to equal the same number. Okay. So grams of carbon divided by 12 for carbon, 12 grams per mole, times Avogadro's number. And this is going to give us the number of carbon atoms. Okay. Atoms or nuclei is the same. These are actually atoms, but um, okay. So that's our activity. So we have our activity now. We have our lambda now. Okay, so what we need to do, sorry for the pause, is we need to find the original number of nuclei and the original activity. Okay. Now we're sort of modeling this or looking at this as a C14 to a C12 process. Okay. But it was never all C14. So basically with carbon dating is you get sort of an atmospheric ratio of C14 to C12. Okay. It's a very small number. 1 out of a trillion, right? So every trillionth carbon atom is a C14 instead of a C12. Okay. Now this number of atoms is not going away in the mass. As it's just changing from one form of carbon to another. So the original number of C14 atoms is the ratio times the total number of atoms. 10 to the 25th. So let's do that. Okay, so we start with that many. So that's our NO. Okay. And now we need R naught. Okay. So we need lambda for a carbon, and I'm sure they gave this somewhere. I'm just going to assume we're given this. I think we did this in the previous problem. Okay. So R naught is just lambda n. I know this is seeming like it's kind of a very extended problem, but when you go through this a few times and see how it works, R naught. So this times that, okay, is our R naught, and then all you got to do is plug this in now. Into t. Again, what we did before, where we say now solve for t is natural log r over r naught negative over lambda. Okay. We know r, we know r naught, we know lambda. Okay, so go ahead and calculate the time. All right, I'm going to stop there.